Hello my dear students and welcome. Chalo, today we're going to tackle a very important topic from Unit 2. It's called potential due to a system of charges. Now I know, the name sounds a little heavy, right? But trust me, by the end of this session, you'll find it super simple. And more importantly, you'll be able to score full marks on it in your exams for sure. So let's get started.
Okay, before we dive into the theory, I have a tricky question for you. A little puzzle to get you thinking. Look at this. If you have a positive charge and a negative charge, do you think it's possible for the electric potential to be zero somewhere in between them? What's your gut feeling? Just give it a thought. All right, so here's the setup. We've got a positive charge, Q1, and a negative charge, Q2. And we're asking, can the potential V be zero at some point P, somewhere on the line connecting them? Now here's the tricky part. The electric field here is definitely not zero, right? Because the field from the positive charge points away, and the field from the negative charge points towards it. So at a point in between, they actually add up. They point in the same direction. So, if the field isn't zero, how can the potential be zero? That's the puzzle we're going to solve.
Okay, to really understand this, let's do something different. Forget the formulas, forget the textbook for just a minute. We're going to build a simple mental picture, a little story. Let's think about this whole concept in terms of hills and wells.
So, I want you to imagine that a positive charge creates a hill in the space around it, a potential hill. The potential at any point is just the height of that hill. Simple, right? So, if you get really close to the positive charge, you're climbing higher and higher up this hill. That means you're at a high positive potential.
Now, what about a negative charge? Well, it does the exact opposite. Instead of a hill, it creates a well or a deep pit, a potential well. The potential value is just how deep you are in that well. So the closer you get to a negative charge, the deeper you go into this well, which means you're at a large negative potential.
Okay, now here comes the magic. What happens if you have both a hill and a well? What's the total potential at some point? It's incredibly simple. You just add the height of the hill and the depth of the well. That's it. Your total potential is just the net height.
All right, so this hills and wells idea gives you a great way to feel the concept, right? Now let's connect this simple picture to the official rule you'll find in your textbook. It's called the superposition principle, and you'll see it's exactly what we just talked about.
So this is what your NCERT textbook says, word for word. By the superposition and principle, the potential V at P due to the total charge configuration is the algebraic sum of the potentials due to the individual charges. Now, out of all these words, there are two that are absolutely key: algebraic sum. So what does this fancy term, algebraic sum, even mean? It means something so simple. Just add them like regular numbers. That's the secret. This is completely different from electric field, isn't it? For electric field, you had to worry about vectors and directions and angles, a big headache. But for potential, it's just simple addition. There's only one rule you have to remember. Just be careful with the signs. Positive for positive charges, negative for negative charges. Okay, theory is one thing, but let's see this in action. Let's solve a quick problem and you'll see just how easy this makes everything. I'm going to show you a simple method you can use for any question like this.
It's a super simple three-step method. Step 1, calculate the potential from the first charge. Let's call it V1. Step 2, do the same for the second charge. We'll call that V2. And step 3, you guessed it, just add them up. V total is simply V1 plus V2. That's it.
All right, let's take a simple example. Suppose we have a positive 4 Coulomb charge and a negative 2 Coulomb charge. They're separated by 4 meters. Our job is to find the potential at point P, which is exactly midway between them. So P is 2 meters away from each charge.
Okay, step 1. Let's find the potential from the plus 4 Coulomb charge. The formula, you remember, is V equals Q upon R. So V1 is K times, and listen carefully, times plus 4 divided by the distance, which is 2. So that gives us plus 2K. Simple.
Now for step 2. We do the same for the negative 2 Coulomb charge. So V2 will be K times, and this is the most important part, times minus 2 divided by the distance 2. You absolutely must use the negative sign of the charge. This is where students make mistakes. So this gives us minus 1K.
And finally, the easy part, step 3. We just add them algebraically. The total potential is V1 plus V2. That's plus 2K plus minus 1K, which gives us a final answer of plus 1K. And we're done. See how easy that was? No vectors, no directions, no complications. Just simple addition.
All right, everyone, listen up. This next part is crucial for your exams. We're going to talk about some common mistakes. I call them silent killers because they can quietly steal your marks if you're not paying attention. Let's make sure that doesn't happen to you.
The biggest confusion, the number one silent killer, is the difference between electric potential, V, and potential energy, U. They sound similar, but they're not. Remember it like this. Potential, V, is a property of a location in space. It's the height of our hill. Potential energy, U, on the other hand, is the energy a charge gets when you place it at that location. So V belongs to the point, U belongs to the charge. Please don't get these two mixed up.
Okay, a few more quick ones to watch out for. First, and I'm repeating this because it's so important, forgetting the sign of the charge. Always include the plus or minus. Second, the trap from our first question. Thinking that if potential V is 0, the electric field E must also be 0. We now know that's not true. And third, mixing up the formulas. Remember, potential V depends on 1 over R, while the electric field E depends on 1 over R squared. These are easy marks to lose, so please be careful.
Great work, everyone. We've covered the main idea, we've solved a problem, and we've even looked at the common traps. Now let's just zoom out for a second, see the big picture, and summarize everything for your revision notes.
So, why do we even bother with potential? Why is it so useful? The answer is simple. It makes our calculations so much easier. Think about it. The electric field, E, is a vector. That means you have to deal with directions, components, angles, parallelogram law. It can get really complex. But electric potential, V, it's a scalar. It's just a number. To find the total potential, you just add the numbers. No directions to worry about. It's a huge simplification. Okay, so for your exam revision, if you remember these 4 points, you are all set. First, the potential from many charges is just the simple algebraic sum of the individual potentials. Second, potential is a scalar, so forget about directions. Third, and this is the most important one, always use the plus or minus sign of the charge. And finally, remember that this whole concept is officially known as the superposition principle for potentials.
And to wrap up, I'll leave you with a final thought to chew on. We started with our analogy of hills and wells, where potential is the height. If potential is the height, what do you think the electric field represents on this map? Think about it. What does the field tell us about the steepness or the slope of our potential hill? It's a really interesting connection, and we'll explore that next time. Until then, keep thinking.